Okay. Welcome, everyone, to a joint M-Cubed and EOL seminar. I'm pleased to welcome Kruse. He's an atmospheric scientist in EOL at the Research Aviation Facility. He earned his PhD from Yale University in 2018, came here as a postdoc afterwards, joint between M-Cubed and CGD, then left for a while and came back about 15 months ago to NCAR. Broadly, his research involves using observations and novel modeling techniques to better understand how processes work in order to improve general circulation models. A primary focus has been gravity wave momentum transport and deposition. Kruse's research interests include atmospheric gravity waves, their parameterization, orographic flows, state parameter observation from aircraft, and atmospheric modeling, both mesoscale and global. Welcome.
Thank you very much for that introduction, and thanks for the invite to give this seminar. I'll mention I was invited a while back to give this seminar, maybe even before CGWaveS, and I was thinking about CGWaveS, so that's what I'm going to talk about today. But as I'll talk more about, CGWaveS was pretty recent. Less than 5 months ago, the project finished, so preliminary is in the title, and that should probably be underlined. This is very recent and very preliminary stuff, so it's going to be, that and speculative. So talk, title, preliminary, look at critical level absorption from convection-generated gravity waves observed during the CGWaveS field campaign. And then lots of contributions from Dave Nolan, Dave Fritz, E. Dye, Tom Lund, Biff Williams, I guess Adam Lund as well, and Jaime and Lars Hoffman. So some intro material, I won't go very deep at all, but in any stably stratified fluid that's real, you often have gravity waves. Within Earth's atmosphere, we think about gravity waves being generated in the troposphere. Let's see if the pointer works. It does a little bit. And within the troposphere, we have mountains, we have deep, moist convection, jet streams and fronts and instabilities associated with them and imbalances associated with them are also significant generators of gravity waves, and shear instabilities on like Kelvin-Helmholtz instability on the small scale can also generate gravity waves. The first three of these sources are typically parameterized in weather and climate models. The way we think about things is the sources are typically, we treat them in the troposphere. They can propagate up and down. If they go down, they might reflect off the surface and go back up. So they're going up. As they go up, because of the reduction in density, you tend to get an increase in amplitude associated with that. And eventually, the waves are going to grow in amplitude and either just cause overturning or some sort of instability mechanism, and they're going to break. What comes along with this gravity wave generation and propagation, gravity waves transport energy and momentum. And this energy and momentum are deposited wherever the waves break, wherever that happens to be. And they're both important. The momentum in particular has been given a lot of attention since, I guess, the early 80s in weather and climate models, and it's quite important in Earth's general circulation. But the key here is gravity waves transport energy and momentum. In terms of impacts, I'll talk a bit more about this. But here's just an example of if you take Wacom and you run it with the gravity wave parameterization, all of the gravity wave parameterizations, and then if you turn all of them off. So this is not one specific source, this is just everything. So if you turn the gravity wave parameterizations off, you can see there's a huge effect, particularly in the middle atmosphere and above. Generally, I would say impacts of gravity waves grow with altitude, but there are still important effects at most levels of the atmosphere. There are direct impacts due to the momentum deposition by the wave attenuation, and then there's also indirect impacts where they can alter the background upon which planetary waves and synoptic scale waves propagate. So they have an impact, direct and indirect, and it adds up to be pretty significant. But again, I'll mention these impacts and the importance of this process is all kind of reliant on parameterizations. So talking more specifically about thunderstorms, Thunderstorms and deep moist convection is also a significant source of gravity waves. In the literature, we tend to think about three primary mechanisms to generate gravity waves. There's this mechanical oscillator mechanism, and the way that I think about it is if you have these parcels going up, turning cape into kinetic energy, eventually they hit their level of neutral buoyancy, probably overshoot, then maybe undershoot and overshoot, and so this kinetic energy hitting the tropopause can be a mechanical oscillator and generate gravity waves. If you have a convective plume in shear, the tops of the plumes can also become an obstacle. You can get flow over and around, very similar to isolated mountains. And this can be a source of gravity waves as well, and you can get mountain wave-like waves coming off of the top of convection. This is sometimes called the moving mountain mechanism. Both of these mechanical mechanisms are ultimately driven by the diabatic heating, which can also directly generate gravity waves. And depending on who you talk to, some people think this is maybe the primary source. So thinking about convection-generated gravity waves in particular, they also have an important role in climate. Where they have their impact is largely where you have the most thunderstorms. So it's kind of in the tropics. And in particular, when it comes to the QBO, convective gravity waves are an important driver of that important mode of climate variability. Convective gravity waves can also influence convection itself. I'm not going to be talking about that today, but that's another interesting topic. So while the biggest impacts are probably in the tropics, and they're very important overall as well, we also have very strong convection over the North American Great Plains. So here's an AIR's gravity wave event climatology. This is for Northern Hemisphere summer. And you can see one of the big global hotspots here is over North America. And yeah, this is due to those really powerful storms that happen so often up here. So gravity waves are relatively small scale. And at current weather prediction models and in climate models, they're under and unresolved. So if we think about the effective resolution of current weather prediction models, it's about 60 kilometers, about 10 times that for climate models. And here's a simulation of T prime at 40 kilometers above some thunderstorms over Florida. These scales are roughly plotted here. So you can see for the climate grid scale, there's so much motion that is completely unresolved. And there can be significant energy and momentum transport within those regions. Even at current weather prediction resolutions, you can see some of the smallest scales are definitely not resolved. Some of the scales are, so it's in the gray zone. So parameterizations are still needed. And then, not going into details here, you could spend a lot of time on this, but these parameterizations are very idealized. Often they're monochromatic. You have assumptions about the phase speed spectrum. In general, they're idealized, they're often tuned, and there's not a lot of observations, especially not a lot of direct observations that are out there to constrain them. So it's really difficult to try and guide them by data. So they're imperfect physically and from observational constraints. So that brings me to the CGWaveS field campaign. This is a field campaign that was in the works for quite a while. I was actually not a part of this campaign coming together. The PIs were Dave Fritz at GATS and Dave Nolan at the University of Miami. And I think this has been in the works since like 2018, 2019. And it was unfortunately delayed by COVID and then by the RAF stand down, but finally happened this last summer. So again, there's the tropical influence, but we also have the strong convection here. And this was really the target of the field campaign. The base was in Des Moines, Iowa. Flights were about 6 to 9 hours each. We had takeoff at 9 p.m. And it was mid-May to mid-June, so just under 5 months ago, the project finished. And it was using the G5. In terms of the G5 instrumentation, here's a diagram of the profile of the atmosphere, troposphere, stratosphere, et cetera. The aircraft was flying at about 12 to 13 kilometers and had a lot of in situ probes on it to measure state parameters, cloud properties, chemical tracers, et cetera. So we have those observations. But some of the observations that make this field campaign unique and really valuable are additionally the lidars. I believe there were 3 lidars that were flown on the aircraft. There was one upward-looking Rayleigh lidar, which allowed temperature observations along 2D sections, which are able to observe gravity waves. Additionally, I believe there were 2 sodium beams, one upward and one slanted forward, allowing sodium densities to be measured up in the sodium layer at about 80 to 100 kilometers. But also there's 2 wind components that Biff Williams is working on getting out of those data. So these are unique instruments and data sets that allow direct measurements at these altitudes where there's not a lot of other measurements. And then another really important measurement here comes from these OH imagers. These OH imagers were looking upward and off of each wing, and they are sensitive to emissions that come from the OH layer, which is centered at about 87 kilometers. The OH layer is part of the air glow layer, so we're kind of seeing this from the ISS in this unfortunately pixelated movie right here. Yeah, that's not coming through so well. Anyway, we've got the 3 cameras, and the field of views project onto the OH layer about like this, and we can see gravity waves. So the emissions are proportional to temperature. Gravity waves perturb the temperature, and so that's how you can see these gravity waves. And here's just a really nice image from the very first research flight where we've got some convection out here, and you can see part of the gravity wave field up in the OH layer. So I have these beautiful concentric rings. So we saw some nice waves. So in terms of the strategy for sampling, convective gravity waves tend to radiate gravity waves in every single direction. Here's T prime at 30 kilometers from an idealized supercell simulation done by Dave Nolan and E. Dye, just recently published. So we can see the outward propagation of these waves in most directions. And the idea was just to fly radials from convection so that we could potentially observe these kind of fields with these upward pointing lidars. And so here's just a vertical cross section, I believe, through the center of this particular supercell. So while that is what we wanted to do, reality is always different and kind of messy. And so here's just a short compilation of some of the research flights, and you can see how the convection evolved and how we were trying to fly radials relative to that convection while it was all moving in real time. Yeah, we had some complicated cases with difficult forecasts, which I'll talk more about, but yeah, we were trying to fly those radials. In the end, we flew 13 flights over 90 hours. There were 90 allocated hours, so we flew 100% of those hours, and we covered quite a bit of ground being based in Des Moines, almost all the way to Canada, almost into the Gulf, covering much of the Midwest and even some of the South. So coming to gravity waves and critical level filtering. So convection generates gravity waves, and we know that we're getting gravity waves that go to the, in every direction. If we just think about east-west, it's generating gravity waves that go upward and to the east and upward and to the west. However, in the summer, in the mid-latitudes, we typically have this wind profile. We have the tropospheric jet, which is westerly, and then we have easterlies that go up for easterly shear and stratospheric easterlies that go up quite high as well. The waves that are propagating up and to the east have increasing wind speed going through them, which tends to increase the vertical wavelength and generally tends to reduce wave steepening and nonlinearity. However, the waves that are propagating to the west have a westward phase speed, and the environmental wind is increasingly westward as well. The level where the wind speed, the environmental wind, becomes equal to the phase speed, this is termed a critical level. And it's critical because, I guess, linear theory kind of blows up at this point. So as a wave propagates up and the environment gets close to the wave, to the phase speed, the vertical wavelength goes to 0, U prime goes to infinity, Richardson number really goes to negative infinity if you want to take it that far, W prime goes to 0. Long story short, linear theory says these waves have to steepen and they have to become nonlinear and they kind of have to break. It's kind of been known for a long time that you have to get really strong attenuation at and below these critical levels. And this research goes way back, even to 1967 by Booker and Bretherton. And I'll just mention also that this is a key part of all gravity wave parameterizations. They all assume when the parameterized wave hits a critical level, you just get 100% complete absorption. So that's all according to linear theory. If we look at this supercell simulation, particularly if we look right here, to the east, we have the eastward propagating waves, large amplitudes, large vertical wavelengths, so should have strong signals to the east. To the west, though, at least in W, the amplitudes kind of go away, short vertical wavelengths, maybe the waves go away as well. And so we should see that difference east versus west. So within this talk, I guess to start with CGWaves, I'm really interested in what's happening to these westward propagating waves. They should go up. They should encounter these critical levels. We have parameterizations that handle this. We have old theory that says what should happen. But here, we'll actually have some data at these altitudes, and I'm curious to know what actually does happen in these observations. So just a few research questions. I'm curious to know if these waves are strongly attenuated in the observations and how completely they go away. At these breaking regions, we should have momentum deposition. And these body forces at a wide range of scales should also be, could also be a source for gravity waves. So is there any, secondary waves above? And with that momentum deposition, I'm always terribly curious about how does the atmosphere respond to this? Does it slow down? How does it respond? Does it get deflected? And this is what the parameterizations are representing. They deposit that momentum, you get decelerations, and one way or another, you get a global response. So I always find that very interesting. And again, with the wind setup, we've got stratospheric easterlies. The altitude range for the Rayleigh lidar, I think, is at the right altitude to potentially see something of what's going on here. Additionally, we have other observations above, so we can potentially see secondary waves. And another, I guess the final reason why I was really interested in the west side is the altitudes at which these waves should be breaking and are breaking according to parameterizations. These are the altitudes that I think are relevant to weather prediction models. These eastward waves might propagate up and out the top of a weather prediction model domain, but the westward propagating waves probably don't. So if we want to go from this data set to better understanding to parameterization improvement to weather model improvement, I think it's kind of the west side is one of the areas where we can do that. So anyway, those are my own opinions. So while we're going to have data, observations are absolutely invaluable, absolutely irreplaceable. That said, all observations are limited to some extent. And I'd say accurate models can vastly extend a data set's utility. Models can be used for convection-generated gravity wave studies, but for the most part, models are never going to get convection in the right place at the right time. with the exception being maybe data assimilation and if you did some ad hoc reanalysis, which others are doing as part of the CGWaveS. So stay tuned for that in future conferences. But if you're just doing free-running forecasts, here's a HER 5-hour forecast for RF7. Here's what actually happened. I'd say this is an excellent forecast, but there are some big differences in location and intensity of the convection, and I think that's going to matter if you want to compare, let's say, this simulation to actual observations. So the approach that I'm using with modeling in this context is essentially I'm trying to derive heatings from weather radar and put that into a model. Really what I'm doing is I'm training a machine learning architecture to emulate a microphysics parameterization given radar observations. So there's still lots of assumptions, but trying to tie it to actual observations to try and get convection in the right place at the right time. So in terms of the method, first thing, I have to train up a neural net. So essentially, I'm getting simulated radar observables, and I'm training up, in this case, a neural network to predict the simulated diabatic heating. Once I have this model trained up, then I give it actual radar observations to predict heating as a function of x, y, z, and t for a particular case. Not showing that here, but then I'm putting that heating into a WRF configuration, and then that heating, then that model can respond to that heating in every way in which the governing equations and resolution allow. Here's W in the mid-troposphere. So you get the convective upward motions, a little bit of compensating subsidence. You can see tropospheric modes of gravity waves as well. But I guess long story short, all mechanisms, I think pretty much all mechanisms of gravity wave generation should be included and be responding to these diabatic heatings. So just some details about this WRF configuration. I'm using a deep, realistic WRF configuration that was validated in the past by myself. The model goes up to 1 Pascal, or about 80 kilometers. But in this case, I'm turning the microphysical heating off. Additionally, I'm using a configuration used in a previous work, but also used by others at Northwest Research Associates. And long story short, I'm combining these two model configurations in order to have a realistic simulation forced by radar-derived heatings. So yeah, again, it's deep top at about 80 kilometers, though we're trying to make that higher. Horizontal resolution of 2 kilometers. Vertical is everywhere less than 500 meters. Fairly large domains, 2,000 kilometer by 2,000 kilometer. I'm using ERA 5 on the model levels to force the initial conditions and the boundary conditions. In terms of the neural network, a lot more could be said here, but in short, it's a neural net. I'm using MRMS, I'm using rain rate, ecotop height, and then reflectivities at 0, -5 through -20 Celsius. And this is being trained to predict the diabatic heating. And it's being trained on free-running WRF simulations in the CONUS configuration from RF1, 9, and 13. And here's, for RF9, you take the radar data, feed it through the neural net, and then height and time integrate for this particular case. Here you can see the diabatic heatings, the integrated heatings for this case. So we had some nice strong storms in Texas and some faster moving storms that spread things out over Oklahoma in this case. Okay, so again, I'm interested in the west side, and I think that's where we'll end up. But the waves should actually grow in amplitude, and they should be big on the east. And we have data on the east side as well. So what do we see there? And I'm also curious to know, on the east side where we should have a big signal, how well does this model configuration compare to the data? So short little case study. Here I'm looking at RF7. You can see we had convection over Nebraska, Kansas, and Oklahoma that was slowly moving east. And here you can see the flight track that we flew relative to the convection. Essentially, we were flying radials centered on central Nebraska and Oklahoma. At the right, here we can see the wind profile from ERA 5. We've got the westerly tropospheric jet, and then we have easterly shear kind of all the way up into the mesosphere. But then we also have this strong westerly shear, positive wind shear above that. So if these waves are going up, this should be very favorable for deep propagation of eastward propagating waves. But the waves might be, the vertical propagation might not be so favorable in this region. So here's the height and time integrated diabatic heatings, so you can see where the cumulative forcing was. And here to get a regional perspective on what was seen from space in this case, these are air's temperature perturbations from averaging and filtering, spatially filtering, a bunch of channels at about 4 microns. And the average vertical instrument filter is depicted by this blue curve. So there's a very wide vertical averaging. There's a lot of vertical averaging that is applied by the sensor. But even still, after averaging all of these sensors and knocking down the noise, here's what AIRS saw for this particular case. You see waves all the way from Texas to the north, generally north and east. Here's a look at some of the lidar observations from this case. Here's these vertical sections were from Biff Williams at GATS. He built the lidar, operated it on every single flight, and also produced these plots. Here we're looking at leg 2, kind of pointed at Oklahoma, and leg 6 pointed at central Nebraska. And in both of these legs, we can see a complicated, but still, I'd say, a pretty clear wave structure. We've got these upward and eastward phase lines, which is kind of what we expect. So we have a nice signal there. If we look at some OH imagery, though, I guess here's what it is. You'll see eventually, because I'll show you more plots here, actually this is relatively quiet. We don't see a whole lot of wave activity up here. Maybe we see some evidence of small-scale instabilities, maybe some very small-scale gravity waves, but as you'll see, this is actually relatively quiet. On the right-hand side here, I'm just highlighting other efforts by those at GATS to simulate from the storm all the way into this OH layer. So they're using their CGCam model all the way up to like 120 kilometers. The upper sponge, the bottom of the upper sponge is at 100 kilometers. That allows them to apply a forward model of these OH sensors to try and get the model to look like the data. So very preliminary simulation, but you can see some similarity between the small scale structures and what we see in the data. Okay, so in terms of this wharf configuration, what did that do for this particular case? Left, we see the radar reflectivity. Right, we're looking at T prime at 40 kilometers. And basically when you see these storms popping off, you see lots of gravity wave activity radiating in most directions in this case. So I guess as a first test, we see waves where we have storms, which is what we expect. If we try to compare that to LiDAR, here's an apples-to-apples comparison, roughly. LiDAR on the left, wharf on the right. I find this a pretty encouraging comparison between the data and this Franken wharf, but it's not perfect. There's other stuff going on in the data that is not represented in the model. Wavelengths are not exactly the same, and certainly the amplitudes are a bit lower. So I'm happy with this very first configuration, but it's not as good as what we had done in the past, basically. If I apply the observational filters from the air sensor to this neural net-driven wharf, we get the plot on the right-hand side. And I'm actually pretty happy with this comparison. You see these kind of small-scale concentric rings in the data. We kind of see that in the model as well. But I have to point out that the color bar for the model is half that of the data. So again, amplitudes are a little bit too low. But it seems like the model is getting some aspects of the observed wave field correct. So I guess my takeaway from that first little case study, just looking at the time, we're good, is that this neural net WRF is imperfect but potentially useful. So now what do we see on the west side? So here's just showing what happened on RF13. RF13, the primary objective was to try and get and sample on the west side of convection. The looping of this simulation doesn't work all that well. But yeah, you can see we're doing these kind of northwest-southeast legs pointed at this central Nebraska convection and even some small stuff in eastern Wyoming. And then we did some legs on a racetrack towards the end of this flight, pointed at this not so strong, but notable convection in west central Minnesota. And in terms of wind profile, similar to before, strong easterly shear all the way up into the mesosphere. So what did AIRS see? Nothing, which is kind of expected. On the west side, we expect short vertical wavelengths. The AIRS sensor has really strong vertical averaging. And so it's not able to see short vertical wavelength features. So not much to see there. Though, yeah, there were waves further to the east. And here's the cumulative diabatic heatings. In terms of the LiDAR, though, we do actually see some waves. Not too large of an amplitude, though the color bar could be changed. But we do see some evidence for these upward and westward tilting phase fronts, which is consistent with westward propagating waves. So we do see some waves in the LiDAR imagery. There are waves there. AIRS cannot see them. Here, I kind of wanted to look for some evidence of critical level filtering. So linear theory and the nonlinear models suggest on the west side, these vertical wavelengths should essentially go to 0. And maybe above that, those waves should go away entirely. So having these plots side by side, they are shifted and scaled so that they are comparable. We do see shorter vertical wavelengths on the west side in RF13 compared to RF7, but the vertical wavelengths are not going to 0. The waves are not going away. So it kind of looks like maybe waves are not being filtered in this case. In terms of the model, here's a comparison between the LiDAR and WRF for, it's this leg right here. There are waves in WRF. They are somewhat similar in structure to what is seen in the LiDAR imagery, but again, amplitudes are quite a bit lower, as we saw in the previous case and as compared to WRF, AIRS, I should say. So I was curious to know why the amplitudes in WRF are too small. And in short, I don't yet have an answer. But the first place that I wanted to look was at the diabatic heatings. So the neural net is trained on free-running WRF simulations. And so here, I just wanted to compare the time and height and space integrated heatings within the free-running WRF simulation and what you get after feeding radar data through the neural network. And in short, if you integrate over this whole domain, time, x, y, z, and t, you get pretty comparable total energy in terms of diabatic heating compared to between the free running and model and the neural net. So the neural net is giving comparable diabatic heatings to the free running model. So I don't think, unless the model's wrong, I'm not so sure that we have too little diabatic heating or too little wave forcing in the model. So I don't really know why the amplitudes are too small. It's not that. Or we have to look more carefully. Other notes, I noticed the convective character was quite different in the free-running WRF simulation compared to what actually happened in reality. There's that difference. And when we were out there in the field, a lot of people, as we were watching these big convective systems, they'd call the system nuclear or that nuclear. So I was curious, is it actually nuclear? So if you integrate over these domains, X, Y, Z, and T, well, forget about the T. Essentially, the energy in this case is on the order of 10 Fat Man nuclear bombs per second. So that's the one that was unfortunately dropped on Nagasaki. So I guess, yeah, it's nuclear. It's a lot of energy. Though if you compare this to the current state of how powerful these things are, it's much smaller than that. Okay, so back to the question of were we actually sampling critical level filtering. So here I'm looking at this neural net force WRF. We've got waves being forced in this region. And if we look at the area where we were actually flying, I would say we do actually see coherent wave fronts propagating away from the convection to the north and even somewhat to the northwest. So that's not consistent with critical level filtering. So we'll have to take a closer look at that wind profile and where these waves are and the phase speeds of these waves. And figure out if they actually should have been attenuated. But at first glance, looks like no. However, if we look further to the south, you can see these phase fronts kind of go to the northwest and north and northeast and east and even southeast. But in this region, we actually don't see a whole lot. So maybe this is where we actually did have some critical level absorption. So here's what the OH imagery looked like on RF13. And I will try to move this around a little bit. Hopefully this works. So if we look at these first images, broadly I would say we see more waves to the north. Things are quieter to the south. On the second leg, I think that's definitely true. We see some waves to the north and kind of nothing to the south. I was curious if this just happens to be a difference between the cameras, but when we change direction, we've got different cameras looking at these same directions, and we largely get the same idea. So once again, here now we're starting to see larger scale waves. Oops, try to pause that. So now we're seeing larger scale waves to the north and still relatively quiet in the imagery to the south. So that's curious. So I guess my first takeaway here is maybe we're not seeing critical level absorption in the radar data, but maybe we are getting an indication via the lack of waves to the south that this was occurring to the south. And that does seem to be consistent with the model, which is encouraging. So now if I let this go forward, just kind of take in the new data. On this northern leg, here we were aimed at convection in west central Minnesota. And we see waves, we see lots of activity. But actually, we're not seeing anything that is, we're not seeing phase fronts in this direction kind of indicating the source being over here. And that might be a result of critical level filtering. The final thing I will mention in this imagery, if we can do this, you might have noticed these vertical stripes all throughout this image. That's going to be really hard to remove. Turns out that was the Northern Lights. On this flight, we were treated to a really spectacular view of the Northern Lights, more photos coming. So no relevance to gravity waves here other than it's going to be annoying to remove that from the OH imagery. But it was a really spectacular part of the adventure. So kind of wrapping up here, I just wanted to acknowledge just the sheer number of people that are required to pull off a field campaign like this. You know, we had the scientific contributions from GATS and University of Miami, Utah State, and Embry-Riddle. And then obviously there was a huge amount of support from NCAR, EOL in particular, but also from M-Cubed and ACOM and NRIT. And within RAF, you know, there's a lot of people there, and everybody had, you know, a really important role to play. The project managers, pilots, aviation maintenance, electrical and aeronautical engineering, technicians, software engineering, and I'm sure this kind of crappy slide is missing some people and some roles, unfortunately. But yeah, a lot of people were required to pull off this field campaign. And I guess just taking a step back, I wanted to appreciate, you know, what we were actually doing here. We had to accurately forecast these storms, which is a challenge because there's not always a lot of predictability. We had to have the accurate flight plans based on these forecasts, which was largely done by Dave Nolan and Cam Pine at Miami. We had to coordinate with those on the ground when we were in the air to take into account changes in the case. And yeah, we had to adjust to changes relative to the forecast and surprises relative to the forecast, and then we had to do that all on the fly, all while avoiding aviation hazards like high ice water content, turbulence, unpredicted cores, icing, etc. And we had to do all of that, and we did do all of that, I would say, pretty flawlessly while flying about Mach 0.8 directly at and away from thunderstorms at night. So just wanted to take a moment to appreciate that. There was a huge amount of effort and planning and preparation that went into pulling this field campaign off, especially at RAF. And yeah, it can be a challenge flying through directly at thunderstorms when things are active and developing. It can be stressful too. Final thing I'll say is that this is really preliminary. It's been less than 5 months since the campaign finished. And data sets are just now coming available. Not everything's available yet, even to the PI group. For example, Jaime at Embry-Riddle provided this first look last night. So not too much to say other than, man, we did see some really spectacular stuff, even on the very first research field campaign, or research flight. So there's much more analysis to be done and many more results to come. Just a preliminary look and overview here. So with that, I'll wrap up and just say, I think CGWaveS was very successful, both from a facilities perspective, as I blabbed on about, and scientifically. This preliminary neural net force wharf configuration, I'd say it looks promising, but I'm not happy with certain aspects, and I would be very interested to talk more with people on how to fix issues. And also I would be interested in talking about the data assimilation aspect of recreating these events and what people think about that. I mean, we are doing that. Dave Nolan and EDI are doing that, but just curious to talk about that. And again, data sets are just coming in, lots more to see. There's 4 presentations happening at AGU in this Gravity Wave session, so if you're going and you're interested, feel free to come there. So with that, I'll leave you with this really pretty photo of the Northern Lights by Cam Pine from an iPhone.
Okay, great. We have time for questions. Oh.
You didn't throw that to me.
No.
Yeah, I'm curious as to why you haven't looked, or maybe you weren't measuring the in situ vertical velocity.
Oh yeah, we were. So we looked at it a little bit. I just haven't quite had time yet to look at that. I've not done the final calibration yet either, so that all needs to happen. In short, we did look at it, and we do see signals. I would say we will have to look at that, and we will look at that, but it is a little bit, I'm not really sure what to expect there, because we're flying at kind of the source level, and we think that a lot of the waves are going upward from there. And so we're just barely getting to the tops of the clouds. And so I say it's a question on what we might see. But we definitely did see some waves. Yeah, in short, there's something there, more to come.
Okay.
Making it easy for Hugh. Yeah, no, really nice talk. I wanted to ask about bringing it back to the parameterizations and, what are your thoughts on what you're doing right now and how that might relate back to our parameterization space for this?
Well, eventually, one thing that I really want to do is once I get this Frankenwurf working the way that I want it, and I have it hopefully well validated, then I can take it and I can quantify the phase speed spectrum. I can really get a good handle on what's actually coming from these waves. And then I can play the game of coarsening the forcing and doing a direct comparison to the parameterizations. We could do that within what is in CESM, but I'd also be very interested in reaching out to those that work on GFS because I'd like to do some direct validated comparisons. I'd like to do some direct comparisons between good modeling and the parameterizations in order to see where there might be deficiencies and try to make an improvement.
Great.
Yeah, that was a very interesting talk for me. I have a question. It looked like all your flight planning stayed away from the source regions, from the convective regions. So you only see what's really far away and not where they originate. Why was that?
So what you don't see here, if I were to show this again, so the aircraft was not always able to get into the stratosphere. I'd say given the triple pause heights, sometimes we could be above, sometimes we could not, kind of 50-50. Often, given the wind shear, we actually had huge, thick anvil blasting off to the east, which you can't see in the radar imagery, but could show you with other plots. And that's potentially an aviation hazard. You can have these, you can have a high concentration of very small ice particles with a total ice water content that's relatively high. And sometimes that can knock out engines. So we didn't want to fly in that. And something that we learned was when we did happen to fly over Anvil and we were close to it, it's quite turbulent. And that was bad for the lidar. So in the end, we had to stay above clouds, and when we couldn't, we just had to stay away from them. And the Anvil was often advecting to the east. So on the east side, we couldn't get that close, though on RF1, here we did actually get pretty close. We were clear. So it depended, but we can't fly everywhere.
Chris, that was a really fascinating talk. Thank you. I was wondering, do you sometimes see gravity waves being originating from two different thunderstorms, and actually the waves then interacting with each other? And
Absolutely.
Could that affect, your analysis of looking for attenuation?
Potentially, yeah. In short, even in this image, I can show a few examples specifically to that. Okay, so if we look here, there we go. We can see those nice concentric rings. Those are coming from the southwestern storm. A little bit later, at one of these, okay, I can't do that so well, but there are these, here's a good source and here's a good source, and both of these sources are generating waves that go up, and you do get constructive and destructive interference. They superpose, and that does really complicate the wave field. And one thing I'll mention in these data, in my WRF simulation, which I didn't show, but I looked at it outside of this, it does look like we have wave fronts coming from two different directions that happen to be over the flight. And so we see maybe some dominant features here, but this might be a superposition of two different sources as well. So it really is important to do a really good job at trying to recreate these cases if you really want to interpret this data and figure out how to interpret it and how it might be useful.
Yeah, it's interesting talk. You converted the WRF reflectivity to a heating profile, right, using the model and neural network. But if the reflectivity in the model has a bias, you would end up with the bias in your heating. Did you look
Yes.
at whether that's possible?
The what, sorry?
Whether it's possible you had a bias or you look at the
Yeah,
range of reflectivities in the observations versus the diagnostic one.
Haven't looked at that. I'm aware of your concern. I have the same concern. I'd say my response at this point is, when we first started doing this, when I was still at Northwest Research Associates, we wanted to stay away from reflectivity because of that. And in the MRMS data set, we wanted to focus on ecotop height and precipitation rate, which I think is well calibrated to ground gauges. Those data are still, I think, the primary, most useful input to the neural network. I wanted, though, to have some information of vertical structure going into the neural net to inform the vertical structure of the diabatic heating as well. So your point is absolutely true. It's an issue, and that might be causing problems. But this is, I guess in short, this is where we started. I hear your issue and don't quite have a solution yet, but.
Well, there may be a way of debiasing it in terms
Sure.
of looking at the frequency spectrum of the model versus the observed.
Sure. Yeah. Great.
Thanks.
I have another question about the parameterizations. So I think in the beginning you motivated this by, where we, even in NWP models with a few kilometer grid spacing, we have to parameterize at least some of these effects.
Yeah.
And I'm wondering, what is the time scale over which the lack of parameterization essentially accumulates model error that feeds back? Is that something that you could tell on NWP timescales, like a few days, or is it something that...
My guess is it is a few days. I don't know. That's an interesting question. Yeah, I do think it would be over a few days. Like if I...
So let's say you're not capturing wave breaking, momentum deposition. Does it matter for a 3-day severe convection forecast?
I would guess not, because it never was accounted for, especially when the models were down low. But I do think, because the models are deeper, now we have this mechanism that we should probably include. I do suspect that it's one way you could improve like 4 to 6 to 7 day weather prediction.
Okay.
So I do see it as more of a potentially improving medium range weather prediction.
All right, thank you.
But yeah, that's a great question. Don't have a straight answer for it.
As tempted as I am to throw it across the room.
Thanks for the nice talk. Perhaps you mentioned this, but I'm curious why you all were flying at night. Was it because of the instruments, or was it because that's when you expected the most wave activity, or none of the above?
It's purely because of the instrumentation. The lidars had to be flown at night. Sunlight. Biff can maybe answer that. We'd probably destroy the lidars.
Camera's even worse. Sometimes we can run the lidars in the daytime, but degraded quality. Yeah, the camera has to run at night.
Yeah, the OH imagers and the lidars not going to give you anything in the day, so just had to fly at night. I'd say I was a little bit concerned. I was thinking the initiation phase of convection is probably really important, and maybe more of a strong generator of gravity waves, and maybe we wouldn't see that as much because we had to fly at night. But we had nighttime initiation too. I wouldn't say it was super common, but we definitely had cases that were very active in the middle of the night in developing. So I think we did get all modes, all phases.
Yeah, we really didn't seem to see a real drop off in the wave activity as the nights went on. Which I haven't looked at the statistics, but it's definitely occurring throughout the night.
Yeah, and MCSs were, like nighttime MCSs were in the proposal, and those are quite common and kind of go all night.
I have a question about those different mechanisms that you mentioned. And you said that you called it, I think, the kind of direct, diabatic heating, which I'm assuming just means you get the compensating substance around the storm. It's not really overshooting, but then you get kind of forced heating around it.
Yeah.
So is one of the main differences just the source of where that is? Like the overshooting is happening higher up in the cloud, the diabatic heating is happening lower down. And given that, does the level of the source region matter very much for what's happening higher up?
It's a great question. I think the answer is yes. I know Dave Nolan and EDI are very specifically interested in that. So the way that I like to think about the diabatic heating, which is not great in this case, but I just think about it as linear perturbations in heating without the full convective circulations, and that alone can directly force the waves. But that's going to be below these anvils, which are giving you these jets of flow outward, and so you might actually be having source generation down here, and that might be affected and influenced by the anvil and the jets with that spreading the flow aloft. So I think the altitude matters. I think the storm structure matters. Yeah, and I don't know. And I'd say what I just said is more of a conversation that came from EDI, who's also working here on CGWaveS.
Okay. Do we have any other questions? We maybe have time for one more. If not, let's thank Chris one more time.